Hello everyone. In last lecture, we have studied the Z-domain description for the discrete time LTI system. We have given the definition of the system transfer function. In this lecture, we will discuss the relationship between the transfer function and the system properties. These properties include the system impulse response, system frequency response, and the system stability. First, we will study transfer function and the system impulse. First, we'll discuss the poles and the zeros for the system transfer function h of z. According to this fraction, we can get this form. It is called pole zero game form. Here, z1, z2 are zeros for this system transfer function. And P1, P2 are poles of the system transfer function. For a causal discrete time LTI system, h of z can be expressed as this pole zero game form. Here, we can find its zeros and the poles. It can be depicted in this pole zero plot. Cross represents the poles. Circle represents the zeros. Now, we will find the impulse response h of k according to the h of z. If we have this h of z, we can get its impulse response h of k. Here, suppose all poles are distinct. Obviously, h of k depends on poles of h of z. Now, we will display the relationship between the impulse response and h of z. When the poles and the zeros move in the z-plane, we can find the impulse response change. According to the system transfer function h of z, we can find its frequency response. For a stable system, we can obtain frequency response h e super j omega. For the stable system, for example, if we have this system transfer function h of z, we can get its frequency response h e j omega. Only the system is stable system. We can use this equation to find the frequency response. Necessary as sufficient condition that our LTI system is stable. If the region of convergence of a transfer function h of z includes unit circle in the z-plane, so for this system, it's a stable system. For this system is a stable system, and this system is unstable system. For arbitrary LTI systems, we can use region of convergence of h of z to determine the system stability. However, if we know the system is a LTI system and a causal system, we can use the poles of h of z to determine the system stability. For the causal LTI systems, if all poles of the h of z are located in the unit circle of the Z-plane, then the LTI system is stable. For example, we have known the system is a causal LTI system, and we have known the system transfer function. Because the system is a causal system, the H of Z has two poles according to the pole's location. As there is one pole, 1.5, outside the unit circle in Z-plane, so the causal system is unstable. We can use the region of convergence of H of Z to determine the system stability. As the system is a causal system, and the region of convergence is outside the circle containing the pole of largest magnitude, the region of convergence doesn't include the unit circle in the Z-plane, so the system is unstable. Here is another example. We have known the difference equation for the causal LTI system. Find the alpha making the system stable and determine impulse response and the frequency response. According to the difference equation, we can get the system transfer function H of Z. Because this is a causal system, so its region of convergence should be in this form. Here, this value is the magnitude of the pole. To make the LTI system stable, its region of convergence should include the unit circle in Z-plane, so the magnitude of alpha should be less than 1. By inversion of unilateral Z transform, we can get the impulse response H of k. This is a picture for H of k. If the system is stable, we can obtain its frequency response according to the H of Z. When the magnitude of alpha is less than 1, the system is stable. We can use H of Z to obtain its frequency response. H E sub j omega. Take Z equals E sub j omega into this expression. We'll find the frequency response. There exists the mutual relationship among the time domain, the frequency domain, complex frequency domain. They describe the system in different domains. If we know one of the domains, we can determine other domains. We can use system transfer function to find its impulse response according to this formula. We can use system transfer function to determine its frequency response according to this formula. But the system should be stable system. In this lecture, we have studied the relationship between system transfer function and system properties. That's all for today. See you later.